Welcome to The Explainer. Okay, let's dive right into this. Today we're embarking on a truly incredible journey. We're going to start at the absolute smallest, invisible scale of the physical universe, and we'll progressively zoom out until we're looking at massive, real-world global impacts. We are literally tracking the journey of materials, from the tiny unseen particles that make them up, all the way to the fuels and plastics that completely define our modern society.
Here's a quick look at our roadmap. We'll kick things off with the building blocks of matter, see how they form compounds and mixtures, and then uncover the magic of metals. From there, we'll look at how we fuel the modern world before zooming way out to examine plastics and our planet. From the microscopic to the global, let's get going.
Section 1. Building blocks of matter. Let's make our very first stop at the absolute smallest scale of the physical universe.
To understand any of this, we have to begin with the atom. An atom is the foundational ingredient of everything around us. According to our source material, all matter, and I mean literally everything you can touch, see, or interact with right now, is made up of these incredibly small particles. And when a substance is made up of only one kind of atom, well, we call that an element.
And this brilliantly illustrates exactly what we're talking about. Take a look at the gold statue and then the iron hammer. If you were to zoom in close enough, closer than the eye can see, you'd find that they are made entirely of their own specific identical atoms. Gold is made of nothing but gold atoms. Iron, nothing but iron atoms. They are pure elements.
But here's the wild part. Atoms themselves aren't just solid little spheres, they're actually made of even smaller subatomic particles. Right in the center, you have the nucleus. That's where positively charged protons and neutral neutrons pack tightly together, both of them having a relative mass of 1. Then, zipping around that nucleus incredibly fast, you have the negatively charged electrons. To give you an idea of the crazy scale here, electrons have a mass so tiny it's practically negligible. And because a standard atom has an equal number of positive protons and negative electrons, the whole thing remains perfectly electrically neutral.
Section 2. Compounds and mixtures explained. Now that we know what a single atom looks like, let's start linking atoms together and see what happens when millions of them combine. As we scale up, things start getting pretty complex. We already know elements are made of just one kind of atom, but when two or more elements combine through a chemical change, they form a compound. Now, the absolute magic of chemistry here is that a compound has completely different properties from the elements that actually made it. Think about water. It's incredibly different from the highly flammable hydrogen and oxygen gases that combine to form it. A mixture, on the other hand, is when substances are mixed together without any chemical change taking place at all. If you mix elements or compounds together, like the oxygen, nitrogen, and carbon dioxide in the air we're breathing right now, each constituent substance keeps its original properties and you can separate them using physical methods.
Now, when a chemical change does happen to form a compound, chemists don't just guess what's going on. They use a very specific recipe. We track this using a balanced chemical equation. So the crucial point is mapping out the steps. First, you write the word equation. For example, hydrogen plus oxygen turns into water. Second, you write the chemical formula. H2 plus O2 becomes H2O. Third, you absolutely must balance the equation so the number of atoms on the left equals the right. So 2H2 plus O2 becomes 2H2O. And finally, you add state symbols, like a little S for solid or G for gas. It is a perfectly organized way to track the entire transformation of matter.
Section 3. The magic of metals. Let's zoom out even further now to see how we're actually building our society. We're moving from abstract chemistry right into the tangible, extracted materials that physically shape our modern world. You might not realize this, but most elements can actually be classified as metals, and they are incredibly useful to us. Unlike nonmetals, which are often dull, brittle, and pretty poor conductors, metals are generally solid, shiny, strong, malleable, ductile, and just fantastic conductors of both heat and electricity. We pull these metals from ores deep in the earth, and we use them specifically for these unique properties. Think about it. We use ductile, highly conductive copper for the electric wires in our walls, and strong, low-density aluminum to build aircraft bodies that fly us across the globe.
Now, what's really interesting about this slide is how we can take a basic metal and completely upgrade it. We call this creating an alloy. An alloy is made by mixing a metal with one or more other elements to give it much more useful properties. Just look at the breakdown for stainless steel here. It's mostly iron, about 70%,
But by adding 20% chromium, 9.5% nickel, and just a tiny 0.5% dash of carbon, you create a material that is significantly stronger than pure iron and vastly more resistant to corrosion. That is exactly why we use it for surgical tools and the cutlery in our kitchens.
The possibilities with alloys are staggering, honestly. By just tweaking the recipe, we get highly specialized materials for almost anything. We mix mostly iron with a little carbon, and boom, we get carbon steel, perfect for motor car bodies. We mix titanium with aluminum and vanadium, and we get a titanium alloy that is super strong but incredibly low density, ideal for spacecraft bodies or even the frames of your glasses. We mix copper and zinc to get brass, which is harder than its constituent metals and perfect for making musical instruments and keys. We are literally mixing atoms to build our world. Section 4. Fueling the modern world. Building the world is one thing, right? But we also have to power it. And to do that, we extract crude oil. Let's shift our focus to this absolutely critical resource. So crude oil is a massive, dark mixture of many different compounds, mostly hydrocarbons. And hydrocarbons are exactly what they sound like. Molecules made exclusively of hydrogen and carbon atoms. But they come in all different sizes. Methane has just one carbon atom, ethane has 2, propane has 3, and butane has 4. Now here is the vital scientific principle you need to remember. A hydrocarbon with a larger molecule size naturally has a higher boiling point. Because these different size molecules have different boiling points, the oil industry can elegantly separate crude oil into different fractions, using massive fractionating towers. Fractions with lower boiling points are lighter. That gives us liquefied petroleum gas, or LPG, for domestic fuels, and petrol for our cars. Somewhere in the middle, we get kerosene for airplanes. The fractions with higher boiling points are darker, more viscous, and much less flammable, like diesel oil for heavy lorries and fuel oil for huge ships. But I really want you to pay special attention to naphtha on this list. Naphtha is a crucial raw material because it provides the essential chemical building blocks for our final topic.
Section 5. Plastics and our planet. We've zoomed out from tiny atoms to the fuels powering global transit. Now, we must take a serious look at the environmental impact of mastering these materials.
Remember naphtha? Well, we take those small hydrocarbon molecules extracted from crude oil and we put them through a process called polymerization. Polymerization is the chemical process of repeatedly joining together many small molecules to build massive, incredibly durable macromolecules. We are synthetically stitching them together in labs and factories to create entirely new materials. We're creating plastics.
Let's move to and see how this builds into the stuff you touch every single day. You interact with these polymerized macromolecules constantly. Polyethylene, or PE, makes your shampoo bottles and cling film. Polystyrene, PS, makes toys and disposable food containers. Polyvinyl chloride, you almost certainly know it as PVC, makes tough drainage pipes and raincoats. Polyethylene terephthalate, PET, is exactly what your disposable beverage bottles are made of. These plastics are lightweight, cheap to produce, and incredibly, stubbornly durable.
But unfortunately, that extreme durability is exactly the problem. Because these metal and plastic products are chemically designed by us to be so strong and resistant to corrosion, their disposal is leading to massive environmental problems globally. Our source material highlights that casually throwing these away severely shortens the lifespan of our landfills. It's causing widespread land and water pollution, and it heavily affects our cityscapes and overall environmental hygiene. The very chemistry that makes them so incredibly useful to us also makes them a permanent, enduring problem for the planet.
So, what's the solution? According to the principles of conservation, the answer is actionable. But it requires conscious consumer habits from all of us. We have to follow the 3 R's principle. Reduce. We need to reduce the use of these materials by buying products with less metal packaging, bringing our own bags to the store, and buying refillable items. Reuse. We can repurpose metal containers as storage boxes and reuse those plastic bags. And finally, recycle. We must practice the habit of properly sorting our recyclable waste. That way, these complex, synthetic molecules can be broken down and used again, rather than just being buried in the earth forever.
We've journeyed all the way from the invisible, perfectly neutral atom, through the fiery extraction of metals and crude oil, right up to the global waste crisis caused by our own synthetic materials. It's a lot to process, I know. So I'll leave you with this thought to consider. From microscopic atoms to massive global landfills, what is the true lifespan of the materials you interact with every single day? Think about the atomic journey of the next plastic bottle you hold in your hand. Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.